All right, this is lesson 2.7, which is a continuation of the study of functions, but we are specifically going to look at something called inverses. The definition of an inverse is in your textbook, but let's take a look at this statement first. It says if a function f is a set of ordered pairs xy, then the changes produced by f can be undone by reversing the components of all of the ordered pairs, thus resulting in the relationship y, x, which may or may not be a function. Now we're going to specifically look at the kind of undoing relationships which are functions. So let me go a little further with what this is saying. If you have a function f of x, we'll look at something pretty easy. It is x plus 2. And I were to look at a set of ordered pairs. If x is 0, 0 plus 2 is 2. If x is 1, 1 plus 2 is 3. If x is 4, 4 plus 2 is 6. There is something called an inverse, and in an inverse, I'm just going to go ahead and tell you that the inverse of this, which is denoted by f with a little -1, what looks like an exponent, but it is called f inverse of x, would be a new x minus 2. What that means is, if I just pick a number for x, let's say I pick 2 and I plug it in, 2 minus 2 is 0. I'm just going to pick another value for x, 3. 3 minus 2 is 1. Pick another value, 6. 6 minus 2 is 4. Look at these sets of ordered pairs. The function increases the x value by 2. Its inverse decreases the value by 2. These are inverses. Look at the ordered pairs. 0, 2, 2, 0. Those are some things to consider as we continue talking about this idea of functions. All right, the definition of a function, and you will use this. Suppose we have two functions, f and g. They are inverses if and only if, when you compose f composed with g of x, if you get x. If you also reverse the composition and do g composed with f of x, if you also get x. If both of these things happen, then f and g are inverses. Something else they mention in this statement is that the domain of f is equal to the range of f inverse and vice versa. You can see that demonstrated over here because these are members of the domain of f, but for its inverse they are members of the range. These are members of the range of f, but for the domain, for the inverse, they are members of the domain. All right, we talk about how to find an inverse. Now I did this process up here, but I didn't explain why, or I didn't show you my steps, and I will in a few minutes. Let's go ahead and start by proving that two functions are inverses. The process is you have to look at f of g of x. You also have to look at g of f of x. If each one of these is equal to x, then you have inverses. So let's start. I have f of g of x. This composition means that I'm taking the g function and I'm putting it into the f function. So it is 9 parentheses x minus 5 over 9 close plus 5. All right, these 9's divide out. That means that I have x minus 5 plus 5 gone. which is equal to x. That's the first statement I'm supposed to prove. Let's look at the composition the other way. G of f of x. From our exercises on composition, I hope you remember that it is not usually, well, it is not a commutative operation. F of g of x is not usually the same as g of f of x, unless they're inverses, and in that case, they are equal and they always equal x. All right, this time I'm going to take the f function and I'm going to put it in the place into the g. F goes into g. So I will have as a numerator 9x plus 5, that's in the place of x, minus 5 over 9. I can simplify first in the numerator. The 5's cancel out. That means that I get 9x over 9. Those divide out and I get x. So I have shown that f composed with g of x is x and g composed with f of x is x. Therefore, they are inverses. My answers here, this one was x, this one was x, therefore they are inverses. Let's do it again with two more functions. These also look similar. I have f of g of x, putting g into f. That's 9 parentheses x plus 9 over 3, close parentheses, minus 3. Now unfortunately this time, when I look at the 9 over 1 and this over 3, 3 goes in there 3 times. They don't cancel out. That leaves me with 3 parentheses x plus 9 minus 3. Distributive property, that's 3x plus 27 minus 3, which is 3x plus 24. That's not x. I already know these are not inverses. All right, but I am asked for this question first, so it's 3x plus 24. If I reverse it and I have g of f of x, remembering how to do composition, I'm going to take f and put it into g. So in the numerator, I have 9x minus 3 plus 9 over 3. Well, that gives me 9x, negative 3 and positive 9 is positive 6 over 3. It does reduce. 3 is a factor of the numerator. It goes into 9 3x times. It goes into 6 2 times. That's the answer. 3x plus 2 is g of f of x. Neither of those were x, and they're not equal to each other. These are not inverses. They don't undo each other. Now this problem uses the terminology one-to-one. One-to-one a function is one-to-one if it has an inverse which is a function. Sometimes something will have an inverse, but that created inverse is not a function. But in number 3 it says the function f of x is x plus 16 is one-to-one. That means they're guaranteeing you that it does have an inverse, and its inverse is a function, and they just want us to find it. So I'm going to go back to those instructions, which are right here. It says the equation for an inverse of a function f can be found as follows. Number 1, replace f of x with y in the equation for f of x. That's going to make for much easier notation. Then, an inverse, the x and y switch roles. So we're going to interchange x and y. We're going to solve for the new y, and it says if this equation does not define y as a function of x, the function f does not have an inverse function, and this procedure ends. But they're telling us in problem number 3 that the original f of x is 1 to 1. That means it does have an inverse that is a function. It goes on to say if f has an inverse function, replace y, the y that you got in step 3, by a new name, f inverse of x. Now we could then prove that they were inverses of each other, but we're not going to. So I will remind you of those steps as we do problem number 3. It says f of x is x plus 16. In order to find its inverse, I will change f of x to y. I have written it in terms of y instead of f of x. So now I'm going to do the step that has me interchange the x and y. So now this is x is equal to y plus 16. I did the interchange. I'm supposed to solve for y. I'm going to make it a little easier by first just swapping sides. Then I'll subtract 16 from both sides, and I have y is equal to x minus 16. This is the inverse function, and I will write it as f inverse of x is equal to x minus 16. Alright, so here I'll just put in the x minus 16. These are inverses of each other. Let me give you an example. If I pick x is 2, 2 plus 16 is 18. So 2 goes with 18. With the inverse, if I pick 18 for x, 18 minus 16 is 2. Now 18 goes with 2. So it does undo. The inverse undoes what the function does. Let's look at number 4. Back to black ink. I have the one-to-one function 2x plus 1. So I have taken, and I guess I skipped a step, I've got f of x is equal to 2x plus 1. Change f of x into y. Now it is the next step when you interchange x is equal to 2y plus 1. Now this step is the inverse, but it's not in the format that I want. So I'm going to just swap sides. 2y plus 1 is equal to x. Subtract 1 from both sides. 2y is equal to x minus 1. Divide by 2. Y is equal to x minus 1 over 2. X minus 1 over 2. I didn't write it, but this is the inverse. F inverse of x is x minus 1 over 2. Now look at the two functions. This one takes the x, multiplies it by 2, and add 1. This does exactly the opposite. It subtracts the 1 and then divides by 2. It does the opposite operations. It does them in an opposite order. All right, number 5. I have, go back to black ink. I have f of x is x to the third minus 5. So I will call it y is equal to x to the third minus 5. The inverse is when I swap the x and the y. Now solve for the new y. I like to just change the sides so that my y is on the left. It's no big deal. Add 5. I have y to the third is equal to x plus 5. Now to solve for y, I need to take the cube root. I do not need to do plus or minus, so I have y is equal to the cube root of x plus 5. If y had been even, y's exponent had been even, I would have to use the square root property. I would get plus or minus. This would not be a function, and I would stop the process. And I would be upset because if that happened to me, that would mean that they told me something that was not true. By telling me it was 1-to-1, I knew that what I would get would be a function, and I will now name it f inverse of x is the cube root of x plus 5. And you will find the cube root symbol in my math lab in the tools, and then we have x plus 5. The f function says cube the x and subtract 5. The inverse says add 5 to x and then take the cube root. Okay, so they do the opposite of each other. And we have one more of those to do. I have f of x is, open parentheses, x plus 3 to the 5th power. So y is equal to x plus 3 to the 5th power. Changing to red ink, swapping my variables, x is equal to y plus 3 raised to the 5th power. I'm going to swap sides. Y plus 3 raised to the 5th power is equal to x. I need to take the 5th root right now. So I will get y plus 3 is equal to the 5th root of x. Now I need to subtract 3. It's not under the radical. And I get y is equal to the 5th root, that's hard to read, the 5th root of x outside that radical minus 3. F inverse of x is the 5th root of x minus a 3. Once again, you will find that root in your tools. The original f function adds 3 to x and raises it to the 5th power. Its inverse takes the 5th root of x and subtracts 3. I hope you can see they are doing opposite operations, and they're doing it in an opposite order. Next, let's talk about something very easy to use. It's called the horizontal line test. And it says a function f has an inverse that is a function, therefore f inverse of x, if there is no horizontal line that intersects the graph of the function f at more than one point. I hope you remember from our very first lesson the vertical line test for functions. Now we're going to look at the horizontal line test, and it is for inverse functions. And if a graph passes the horizontal line test, then it will be 1, 2, 1. So a graph that has a function an inverse function that passes this horizontal line test, then it is called one-to-one. Let me see if I can maybe make that a little bit clearer. I think I will switch over to my red. All right, this is a function. They don't ask us to do it. They tell us it's a function. Well, we knew that anyway because it passed the vertical line test, but we're not checking that. We are checking to see, does it also pass the horizontal line test? And the answer is yes. This graph is a function that has an inverse. They don't ask this question, but it is one-to-one. Back when we first studied functions, we said the definition of a function was a relation in which each x had only one y. Well, now a function is a one-to-one function, 1 to 1, if each x has one y and each y has one x. So it goes both ways now. All right, number 8. Here is a graph. It is a function. Does it have an inverse? Well, let's see. Nope. It just failed the horizontal line test for that particular horizontal line. So that's no. This function is not 1 to 1. That is another way of saying this function does not have an inverse function. Number 9, use the horizontal line test to see if it has an inverse, and the answer is yes. All right, number 10. Number 10 says use the graph of f to draw the graph of its inverse function. All right, what they mean by that, they did not give you this equation of this line. You don't have f of x is equal to. All you have are some ordered pairs. So for f, I'm going to write the ordered pairs. This one down here is -2, -2. The next point is -1, 0. The third point is 0, 2. Now if I'm going to try to graph f inverse, what I need to know and remember is that the x's and y's, the domain and the range, will swap. You can't see any swap in the first point because they were equal. The second point, it is 0, -1, is an ordered pair on the inverse. 2, 0 is an ordered pair on the inverse. Using your graphing tool, you will choose the line tool. You can only plot 2 of the 3 points. It doesn't matter which 2. So if I take the first 2, -2, -2 happens to be the same point. 0, -1 is right here. Now that's all my MATLAB will allow me to do. But since I'm just doing this on a piece of paper, I can put a third point. This is the line, and I'm sorry it's not very straight, that is the inverse. Now, something that I've not said, but it's very important to know. These two lines are reflections of each other, not about an axis, but about this line that cuts right through the middle of the first and the third quadrants. It is the line y is equal to x. It is the identity line. And on this dotted line are the points 0, 0, 1, 1, 2, 2, 3, 3, and so on. Inverses are reflections of each other about that line. All right. This one says, given the function f of x is equal to 5x minus 7, find f inverse. Let me switch back to my black ink. Maybe. There we go. So how do I find the inverse? Remember, f of x is equal to 5x minus 7. Y is equal to 5x minus 7. I'm about to do the inverse right now. X is equal to 5y minus 7. I'm going to swap sides. 5y minus 7 is equal to x. I'm going to add 7. 5y is equal to x plus 7. Divide by 5. And y is equal to x plus 7 over 5. F inverse of x is x plus 7 over 5. Now if I were to graph that, I would call it 1/5 x plus 7/5. And all I did just then was put the x over the 5 for 1/5 x, the 7 over the 5. All right, so the inverse, that was my first step. You are welcome to put it as x plus 7 over 5 or 1/5 x plus 7 over 5. This would be putting it in slope-intercept form. It says choose the correct graph. All right, this would be easier if these were enlarged, but they're not on this little piece of paper. So let's talk about the original function. It has a y-intercept at -7 and a positive slope. So, and that one will be, f will be solid. Does this have a y-intercept of 7? No, that can't be right. Does this have, it wasn't 7, it was -7. Does this one have a y-intercept of -7? No, it can't be right. Does this one have a y-intercept of -7? Yes, and so does this one. So both of those seem to have the f function correct. Let's look at f inverse. It has a y-intercept of 7 over 5, and I don't usually like to have intercepts that are mixed numbers. That's 1 2/5. All I have to know is that that's a positive. And that's a dotted line. Look at this y-intercept. Can you see that it's negative? That can't be right. Is this y-intercept between 1 and 2? Yes. Also, this dotted line has a positive slope. This dotted line had a negative slope. So I matched my two lines with this graph. It says the domain of f is blank. Well, f is a line. It is this solid line. Its domain is all real numbers. It is from -infinity to positive infinity. And if that's the domain of f, it will be the range of f inverse. Well, the range of f is from bottom to top as opposed to the domain, which was from left to right. It didn't go very far left to right, but it was all real numbers. Its range is also all real numbers, and so the domain of the inverse is all real numbers. This one didn't shed a lot of light on this. These two must be the same, and these two must be the same. They just happen to all be all real numbers. All right, this one will not have the same kinds of all real numbers for the domains and ranges. The original function is a squaring function that has been shifted down 7, transformation, but it has a restricted domain. So I'm not looking at these graphs down here. I just want to talk about for a minute what it looks like. It looks like, remember, pull down 7. So I'm going to say it's been pulled down here. Now normally it would look like this. But they're restricting the domain and saying this graph, but only when x is greater than 0. So I don't get all of that. Let's say that's -7. All I get is this piece. The other one was not 1 to 1. It would fail the horizontal line test. This graph passes the horizontal line test. I'm supposed to find its inverse. So how do I find its inverse? I say y is equal to x squared minus 7 when x is greater than or equal to 0. I'm going to swap. X is equal to y squared minus 7. Well, I swap it in this also and say y is greater than or equal to 7. This graph has a domain restriction. This graph has a range restriction. Solve for y. Y squared minus 7 is equal to x. Y squared is equal to x plus 7. Now, typically I would need to use the square root property. I'm going to write something and erase it. That would say y is equal to plus or minus the square roots of x plus 7. I don't do that. I don't do that part of it because I have this restriction y has to be greater than or equal to 0. So I don't keep the negative. So this is f inverse of x. It's the square root of x plus 7, and it does have a restriction. But I don't write the restriction here. It is square root of x plus 7. Now we know from our study of transformations that this is a square root function, which is kind of a branch, and because it's added 7 on the inside, it's going to shift left 7. So I'm going to say that's -7, and the branch, I'll do it in dot, is going to do like that. So I've already begun to use what I learned about transformations, and as I look at these, I can see that choice A is the right answer. But I have some other questions. It wants to know about domain and range. Well, for the original function, the domain, which turned out to be the range of the inverse, both of them, it says to do it in interval notation. Both of them go from 0 to positive infinity. Let's take a look at that. The domain of this one is from left to right. The leftmost x is 0. The rightmost x, well, it goes on forever to the right. That's where I got the infinity. For this graph, its range, its y values, its bottommost y value is 0, and it rises forever, so it's 0 to infinity. Now let's take a look at the range of f. All right, this one is f. Its range is from -7 to positive infinity. -7 to positive infinity. Let's see about the domain of the inverse. That's this one. Its x's are from -7 to positive infinity. Okay? Now, these last two have you thinking about inverses, possible inverses, with ordered pairs. And I started this lesson a little bit with this, but let's talk about compositions with ordered pairs. We've not really done that. This says f of g of 7. Start with the inside. G of 7. Go to the g function. This is g function. This is f function. You can tell right here. Go to the g function. 7 is an x value, it gets acted on by g, and its g of x value is -4. That's the inside. Now I want to go to the outside f of g of 7. Well, what I'm really saying is f of, what is g of 7? It's -4. What is f of -4? Go to the f function. There's -4. When the function acts on it, what does it return? 7. Now, you might not be in awe of that, but I started with 7. I went through the g function, took that value, put it into the f function, and came back to 7. That is a characteristic of inverses. Remember, f composed with g of x is equal to x if they're inverses. So f of g of 7 is equal to 7 if they're inverses. This one says g of f of -4. So if I write it in the other notation, g of f of -4 is equal to something. Now, if these are inverses, I guarantee you I'm going to get -4. But I don't know if they're inverses. It doesn't say they are. These are my f values. This is what happens with the g function. Start with the inside. F of -4. -4 goes to 2. So now I want to find g of f of, well, that's already written. I don't need to write that again. G of f of -4. F of -4 is 2. Let's go to the g function. It's not -2, it's 2. G of 2 is -2. That kind of looks strange. So I found f of -4. I got 2. Then I find g of that, and I got -2. These two functions are definitely not inverses, because when I did the composition, I started with -4, but I did not end with -4. So if two functions are inverses, if f and g are inverses, then f of g of any number, let's say 5, even if I don't have any ordered pairs, it's equal to 5. G of f of 7, if they're inverses, is equal to 7, because if you do the composition for inverses, they unwrap each other and you end up with what you started with. Okay, I hope that helps with the study of inverses.